Today we are discussing a new mathematical tool that works in all subjects where normal calculus applies. We are starting with introductory lecture in a series to be followed for master and PhD students, faculty members or scientists desirous of thesis, guide or research in any discipline, in any institute of the world using this approach. So this is the paper we are discussing, part of the paper. This was published in Taylor Francis Open Access YY-Calculus from Soil Consolidation to Other Physical Sciences. So these three authors, Sudhir K. Tewatia, myself, I was professor in Adama Science and Technology University, Ethiopia, at that time when we sent this paper for publication. Kanish Tewatia, Antriksh Tewatia. Kanish Tewatia is from Canada, Toronto. Antriksh Tewatia is working in this Hughes district, Gurgaon. So this is the introduction. Professor Sudhir Kumar Tewatia. I was former Vice Chancellor, President, Director, Dean, Principal, Professor, Scientist, Consultant, etc. in India and abroad. He is Kanish Tewatia. Kanish Tewatia is BTech from NIT Kurukshetra and PG in Artificial Intelligence from Loyalist College, Toronto, Canada. Antrish Tewatia is BTech Computer Science from Guru Gobind Singh Indraprasth University. So one line summary of the paper is, this originated from soil consolidation. Soil consolidation for the people who do not know consolidation, who are not civil or geotechnical engineer. So in a scientific term, it is hydrodynamics, soil consolidation. It's a mixture of hydrodynamics and creep and diffusion. Diffusion equation that is governed by Fick's law. So it's new approach in calculus or mathematics to explore the research and development in physical sciences wherever Newton, Leibniz or common calculus applies, gets complicated or fails. So this is the, let me introduce first what is this Newton calculus and what is this new approach. This Newton Leibniz, when they suggested the calculus, and that continues till today with some variations, like half differentiation or so many other things introduced after that. But this approach, this side dy by dx y dash, or this side x, that dy by dx is a function of x, that remains same till today. So here only we have changed this x axis. It remains same, dy by dx. Here we have changed it to y, or we have reversed it, y this side and dy by dx this side. That is the basic difference between these two approaches. So advantages in soil consolidation are discussed and further improvement proposed with particular reference to Tewatia's YY- approach in calculus, that is called settlement versus rate of settlement approach in consolidation. This y is settlement in consolidation and rate of settlement is dy by dx. So it is known by this in consolidation. The branch of calculus named as YY dash or y versus dy by dx is suggested as compared to the common xy dash, x versus dy by dx versus x, or Newton Leibniz branch, this one. That solves some complicated unsolved theoretical and practical problems in physical sciences. Physical sciences are physics, chemistry, mathematics, biology, allied sciences, all engineerings, almost astronomy, cosmology, whatever, metallurgy. So in amazingly simple and short manner, particularly when independent variable x is unknown and xy dash approach cannot be used. Here in this, dy by dx is a function of x. So if x is unknown, this is unknown. This cannot be used. Let's go further before I'll come to it again. So complicated theoretical and practical problems in 1D, 2D, 3D. D means dimension. Primary and secondary consolidations with non-uniform gradual loading and irregular shaped clays are solved with elementary school level YY dash approach. That means very simple, not complicated. Some particular cases from soil consolidation that are basically creep and diffusion equations in isolation and in combination with each other are taken for comparison with heat and electricity transfer. Why we are comparing consolidation with heat and electricity? Because heat and electricity, heat is thermodynamics, consolidation is hydrodynamics, and electricity, that is electrodynamics. All are using diffusion equation. What is diffusion equation? In diffusion equation, we have a thrust, a force that drives. In hydrodynamics, that force is water head or pressure. In material science, it may be pressure. And in thermodynamics, it is temperature that drives the heat. And in electricity, it is the voltage that drives the current. So one is driving force, one is the quantity that flows. In hydrodynamics, the water or pressure flows. In thermodynamics, heat flows. In electricity, current flows or charge flows. And third component in this is some conducting part, that is resisting or conducting. In electricity, we directly call it electrical resistance or electrical conductivity. In thermodynamics, we call it thermal conductivity. And in hydrodynamics consolidation, we call it hydraulic conductivity of the soils. So YY dash approach can similarly be tried in wave equation. That is just opinion that we can try there also. So far we have tried it in diffusion and creep equations, wherever normal calculus works or fails. So this is now introduction. What is common xy dash and new yy dash calculus? So the xy dash approach in calculus was invented by Tewatia in 98 and used in various theoretical and practical problems of soil consolidation. This is given references 1 to 22. I have given total 33 references. Out of that, 22 are on this approach only. And they are basically I am involved in all of them in 22. In common calculus, differential equations are used for solving problems mostly as below. These are the differential equation. F is a function, y is a function of x, y dash or dy by dx is again a function of x, f1x. Then double differential y double dash is equal to d square y divided by dx square is equal to f3x is again a function of x. That means differential equations are used as a function of x or vice versa. This is common x y dash calculus here. It may be here instead of y dash, it may be y double dash also. So when independent variable x is unknown, the x y dash calculus fails or cannot be used, because all of these y dash, y double dash and all these, they are function of x and x is unknown. So this fails. Y dash calculus uses y in place of x. So simple, here in place of x, y dash uses y. That is the simple difference, basic difference. So how this idea generated? This idea generated around 96 or 95 in that in the 90s. So idea generation and need of xy dash approach in calculus. So in consolidation, all researchers were using delta t or delta sigma plots, where delta is settlement and T is time and sigma is pressure. It is rather effective pressure. That terminology uh, uh, that is more relevant for the geotechnical engineers. Otherwise, for the common people, we can assume it as a pressure. So, settlement is a function of time, and settlement is a function of pressure on the soil or on the clay, saturated clay. When we apply pressure, more pressure we apply, more is the settlement. And once the fixed pressure is given, then with time it keeps settling with time. It's a function of time, settlement. So it is a function of two things: settlement, pressure, and time. So the solution failed when T or sigma is not known. Like in this earlier approach in the calculus, I showed when x is unknown, so then what we'll do. So similarly, when time was unknown or pressure was unknown, so this solution failed. And that was the usual case in the field. Incidentally, it was a usual case. Time and pressure that was not correctly known. All equations were based on that only, that this time it started, or with this pressure it started. The average time of loading concept in case of continuous uniform loading, that was, however, was very rough assumption and not true. In this case, suppose this consolidation is in progress, at the same time load is also increasing. So Terzaghi was the father of soil mechanics. Basically, or he was a mechanical engineer teaching thermodynamics, and he used the heat equation with some modifications in consolidation. So this he suggested that we can take average time, that at this time this was the time of loading, but it proved to be incorrect. In various papers it has been shown. So now what are the advantages of YY dash calculus in consolidation? So because it started with consolidation, soil, so let us start with that. What are the advantages? In the field, settlement is due to complex phenomenon like primary means diffusion equation, secondary consolidation means creep. They intermix. When we obtain the data in the field, it is not exactly due to primary consolidation, or not even exactly due to secondary. They are intermixing settlement. So it was a problem to filter them. Non-uniform gradual ramp loading, multiple stratified layers with different consolidation properties, complex drainage, irregular haphazard boundaries, unknown initial time, pressure and settlement at the instant of load increment. In such situations, YY dash approach gives easy solutions of some theoretical and practical problems. So parallel to that, advantages of YY dash calculus in all sciences and engineering. Based on the progress in consolidation and now beginning in the thermodynamics, electricity and other fields, in my opinion, addition of new YY dash calculus with the normal XY dash calculus is like the comparison of Hubble telescope with James Webb telescope. It gives high resolution power for analysis and solutions. Now let us see where it gives high resolution. Any example? Yes, it is there. So examples of consolidation in the field, like it resolves the Terzaghi's one-dimensional equation in 3 accurate components instead of 2 known earlier. They are parabolic and exponential. So U is degree of percent of consolidation. So earlier 2 components of Terzaghi's equation of consolidation, that was basically a diffusion equation, almost similar to heat equation. So in that only 2 parts were known, as it can be seen easily. I show you that graph, that this is the plot of time, this is the plot of time, linear plot versus U. So above this part up to 60% or something like 40%, it looks to be a parabola. So I think I should rub it off. Now it is clear. So I draw this. if I draw this equation also I show what it comes after derivation like heat equation. Basically, this is the equation that comes, and for 60% it approximated with parabola. T is related to u, T is equal to pi by 4 u square, and remaining part, this is exponential. How we guessed it and how it came. So this can be seen from here. For this part up to 60% is looks to be parabola. Parabola is like this, and exponential part is like this. So this is exponential, goes above is parabola. So by looking it roughly, it can be seen. However, when we plotted u versus dy by dt, dy by dt is y versus y dash. Then it gave this symmetrical curve on log, and the straight line, and then this curve. So this is linear, this is log. On log, this ut plot was like this. It is S curve but skew symmetric. But u versus du by dt, this is symmetrical curve from here and here. And this further, this is enlarged portion of the symmetrical curve. This symmetrical curve goes like this and it retraces itself like this. This is inverse mirror image of this, theoretically. But in practically, in the field, we find this because creep is mixing. So it gave the new, when we compared these equations, these two, this is parabola, this is exponential. So earlier in mathematics, it was not the concept that when we plotted this, it is coming inverse image of this. It gave the new concept in mathematics, how parabola and exponential functions can be viewed as inverse mirror images of each other in YY dash approach. And this property was used to filter creep and diffusion settlements from the mixed data here. So this is the one of the examples how it gives more resolution power. Another is it resolved consolidation quantitatively into 6 phases. Earlier it was resolved in 3 phases, that too not quantitatively, approximately. People guessed, okay, yes, after this it may be a creep, after up to this people guess like somewhere it starts creep, somewhere here it starts creep, but with exact quantitative isolation was not given by anyone earlier. Here it divided, this divided into 6 parts instead of 6. So this is high resolution. Basic theoretical equations of vertical and radial combined 3D secondary consolidations for complicated drainage, non-uniform ramp loading, etc. were derived in simple and short manner. Many other advantages are summed up in the book. There's a full book written on this by authors Sudhir Tewatia and Kanish Tewatia, who are the author of, Kanish Tewatia is author of this paper also with me. So that book is freely available on the ResearchGate based on the publications in the most prestigious international journals. It can be searched by googling Tewatia on consolidation. The slope at any point on this curve was just this settlement, equal to this settlement. Similarly, from this side, if we count from this bottom, the slope of this curve from bottom at any point is again equal to this height. The more is height, more is slope. So this is again an interesting property that was used to find the corrected zero settlement and the final settlement of the consolidation. And by using this method, YY dash approach, we could reduce the time of the test of this consolidation from 1 week or 2 week to almost half an hour or even lesser. Theoretically zero, but practically we have to take some points. How? Because for evaluating the coefficients of consolidation and initial and final settlement, now we need not draw the full curve and conduct the whole experiment. Just around this point, only this much part can predict the initial and final portion and the later portion of this plot. From this we can find from the slope the initial settlement, the final settlement, and the coefficient of consolidation using these equations. Earlier we were using these equations, we were using time T50. When time of load increment is not known, then this T50 is not known, so this could not be determined. Now we had the new formula. We could use this settlement versus rate of settlement, the slope of this curve. This gives coefficient of consolidation, CV. And further resolving or further clarifying this, the slope of this plot is equal to u, or this u above this or u below this, is by this curve. We are plotting the slope of this curve, that is settlement versus rate of settlement, delta versus d delta by dt on log scale. Then slope of this curve is again plotted versus this u here. So that gave this very clear picture, 0 to 40%, 40 to 60 to 100%, in between transition curve. So this was in diffusion equation, and this was applied for any shape. Earlier the specimen of the testing specimen for consolidation was cylindrical or cubical or parallelepiped. Suppose it is irregular, it doesn't have any shape. So then this was also formula given that could determine coefficient of consolidation and ultimate settlement delta 100 for any irregular shaped specimen. Then in creep, coefficient of secondary consolidation, that is the coefficient of creep, that is slope of settlement versus log time plot. Now as you know, the creep proceeds linearly on y versus log of time plot. Suppose I do not know the time of load increment, suppose I do not know that this time, so I cannot start from any point on log plot. On linear I can start, okay, let's start from here, remaining can be subtracted. On log I cannot do. So solution for that also was given by this plot, and by this plot also similarly following that, let me read it first. A rough, not exact example is Pisa Tower, where it is assumed that it has been sinking due to secondary consolidation since its construction in stages about 8-9 centuries ago. So exact time of final present load increment is not known. However, time settlement data of last 100 years is known if one wants to predict its past and future settlements due to secondary consolidation and wants to determine the coefficient of secondary consolidation using creep or secondary consolidation equation without taking sample from its foundation, just by observing the settlement of any structure. I am just taking the name of Pisa Tower, but this is not the exact example. Suppose some structure is already settling in the field due to creep. So just noting the settlement of the structure itself without taking any specimen sample from the foundation, we can determine the coefficient of creep and future and previous settlement of that structure. using YY dash approach. Here is the example. I have this data, this small data, that is delta versus d delta by dt or inverse of that, dy by dx or dx by dy. So from this delta versus d delta by dt, that means y versus y dash, I could find y and t plot. So it is worth thinking, again a point of thinking or research, whether it is graphical integration, because we are obtaining from YY dash plot, we are obtaining YT plot. Similarly for pressure, earlier we were plotting settlement versus rate of settlement with respect to time. Now we are plotting settlement versus rate of settlement with respect to pressure. D sigma by D delta or D delta by D sigma, and similarly we are obtaining this plot as in case of time, simply T is substituted by sigma. Remaining procedure remains same. Now we have some parallel and analogies, examples in diffusion equations of physical sciences, say thermodynamics, electricity. Okay, I am taking this example. A solid body of length L, breadth B, height H was allowed to cool for a sufficient time, theoretically infinite, from temperature T degree centigrade to 0 degree centigrade. In an ice box at 0 degree ice temperature, total ice melted 0 degree centigrade was 100 ml due to latent heat gained from the body while it cooled. Now suppose in T minutes time. Okay, that simply means that some body is inserted in ice and some energy or temperature is dissipated, and that is equal to the melting that is equal to the energy consumed in melting 100 ml of ice into water at 0 degree centigrade. So let's say, like, when it is this body is insulated around like this, and it is dissipating only along length, this face and this face. So in time t, it is ice melt is 20 ml. Similarly, now we are insulating like this, and like it is flowing with the sides, two sides. Then it may be say it is 80 ml. Then with top and bottom, like length, breadth and height. So two faces, two faces, two faces. So individually they are given like this. So find the total ice melted in T minutes, same time, when the heat conduction is allowed along L, H and B simultaneously from all six faces, and no insulation is provided. So this YY dash derived equation is used directly. So this equation is 1 minus U LBH is equal to 1 minus UL, 1 minus UB, 1 minus UH, where UL 20 into 100 is equal to 0.2, UH is equal to 80 by 100 is 0.8. So this equation is derived with the very elementary knowledge of this thermodynamics or hydrodynamics, or in case of electricity, it may be derived with the normal calculus also, but it is much easier in this case, and it requires almost no knowledge of the subject. Then electrical wires of different conductivity resistance are connected to two capacitors with charge or voltage difference U. When connected individually, they drain 10, 20, 30, 40, 50% U respectively. U is percentage of the charge drained, total charge. How much percent charge they will drain in time t, same time, when they are connected in parallel. Now voltage difference is not constant, it drops as current flows. Please do not compare it with the battery. Their voltage is constant even if current is flowing. That is similar to that thermodynamics example. Using this, it is calculated like this. It is interesting to note that derivation of equation 1, this equation with YY dash approach, is very simple, requiring just elementary or even lesser knowledge of the subject. like hydrodynamics, thermodynamics, electricity, etc. These are given in the publications, this Tewatia and Tewatia 2019. Then this question 1 for heat equations, they are further solved. They are using this heat equation, consolidation equation, etc. That is simply to show the parallel analogies in these two, thermodynamics and consolidation. And formula of one or equation of one can be used similarly in the other. As I earlier told, that hydraulic head that can be compared with the temperature. In electricity, it can be compared with the voltage because that drives. So some more example, I would expect you to go through all this, and in the next lecture we shall discuss them in detail. So similar examples can be taken in material science, ionization, dissolution of salt in solutions, intermixing of gases, mass transfer, astronomy, cosmology, etc. One interesting example is Hubble's law, where plot of distance versus speed of galaxies uh, is straight line and slope of that is Hubble constant. Plot of settlement versus rate of settlement in radial consolidation is also a straight line. It is shown in figure above, the slope of which is CR, coefficient of radial consolidation. It starts from the beginning and reduces the experimental time to the minimum possible, 0 theoretically. Creep examples are found in various engineering and physics. Spreading communicable diseases like corona, etc. is also a diffusion where YY- approach may also have some applications. Now let us come to some references, publications. On this, following publications are available in the literature, mostly by me, all as first author or single author. This is the book. This website is given for the book and research gate up to 22. This two publications by father of soil mechanics, Terzaghi. Then this Leo that is solved using this calculus, some complicated problems in the consolidation. The similar problems can be solved very easily compared to this by using YY- approach. Then this is Fick 1855 on liquid diffusion. Then Fourier, everybody knows Fourier. Then Carrillo, he worked on 2 and 3 dimensional cases in theory of consolidation, barren radial consolidation. Theme is for the aquifer, when groundwater flows in the well, that is also a diffusion because the driving force again is water head, that is radial flow. Then Biot 3D consolidation, and this is thesis published by even MSc thesis. So that's all for today. We shall take up in detail in the next lectures. Thank you.